Every day, thousands of passengers board flights at Los Angeles International Airport, bound for the other side of the planet. Their destination is often Tokyo, a journey spanning over 5,000 miles of the Earth's surface. Looking at a flat map projection, the shortest path looks obvious, a straight line cutting directly across the Pacific. But that direct path is never flown. Commercial flights take a sharply curved northern route that hugs the Alaskan coastline instead of crossing the deep ocean. Modern airplanes carry more than enough fuel to traverse the Pacific, and their engines provide the raw power necessary to handle the distance. The real reason planes detour so far north involves an invisible set of regulatory and geographical walls that dictate exactly where commercial aircraft are allowed to fly. It is a common intuition that safely crossing a massive body of water requires an aircraft with an excessive number of engines for redundancy. You can see that logic reflected in this AI-generated image. The artificial intelligence hallucinates extra engines and even a second sun, operating on the assumption that sheer power is the only way to solve long-haul flight. The actual challenge lies in the oceanic vacuum. These are vast sectors of the Pacific Ocean where infrastructure vanishes and the horizon offers no landmarks. The greatest risk in transoceanic flight is being forced into an emergency descent over a region with no land in sight. Modern aviation eventually bridged the Pacific not by adding engines, but by establishing strict mathematical limits on time and distance. For decades, aviation regulators enforced a strict 60-minute rule. It legally prohibited any twin-engine plane from flying more than 1 hour away from a suitable landing strip. That single regulation mandated the use of massive 4-engine aircraft, like the Boeing 747, for any flight crossing an ocean. Then, turbine engineering reached a new peak of reliability. Manufacturers created engines capable of running for tens of thousands of hours without a single failure. To account for this leap in engineering, regulators introduced ETOPS, or Extended Range Twin Engine Operations Performance Standards. ETOPS serves as a regulatory license to be isolated over the ocean, granted only to aircraft that prove a specific, verified level of mechanical reliability. This shift moved the focus away from the number of engines and toward the measurable reliability of the systems keeping them running. ETOPS creates a precise safety radius around isolated diversion airports, like the runways here in Honolulu. As ETOPS ratings increase from 60 to 300 minutes, green safety zones expand from coastal cities. For a flight to be legal, these circles must overlap, creating a continuous safety corridor from the U.S. West Coast to Asia. The extreme northern curve of the Los Angeles to Tokyo route exists to keep the plane within the path where these safety circles are at their thickest. Every trans-Pacific flight path is a mathematical tightrope. Even in the middle of the ocean, the plane remains leashed to a runway it can reach within its approved time limit. There is still one place on Earth where the ETOPS equation fails completely: the geographic South Pole. The South Pole lacks usable emergency runways, while its extreme environment creates a physical blockade that actively threatens critical flight systems. Extreme polar temperatures can drop low enough to freeze standard jet fuel, while dense polar radiation often disrupts vital navigation equipment. Because the isolation is so absolute, any emergency landing on the ice would be a terminal event, as search and rescue operations are physically impossible to mount. Engineering and mathematics allowed us to map safe routes across the vast oceans, but the poles remain a reminder that extreme geography can still close off parts of our planet.